Welcome to week 4 in our course Analysis of a Complex Kind. Today we'll learn about inverse functions of analytic functions. We'll learn that these are themselves analytic under reasonable assumptions. As a motivation, let's start with a logarithm function. The logarithm function is going to be an inverse of the exponential function. So to remember things, let's remember what the exponential function does. Remember, if w is of the form u plus iv, then e to the w was defined to be e to the u, and that's our regular exponential function from real analysis, times e to the iv, where e to the iv simply stands for cosine v plus I sine v. And again, these are the real valued cosine and sine functions. So with that in mind, suppose we have the following problem. Given a certain z in the complex plane, not the origin, find a w in the complex plane such that e to the w is equal to z. In other words, we want to start with a z over here in the z plane, which is not the origin, and we want to find a w in the w plane such that the exponential function maps e to the w to z. So this point w is to be mapped to z under the exponential function. So what we're looking for is an inverse to the exponential function. The exponential function maps w to z. We're looking for the function that starts at z and finds the w that under the exponential function goes back to z. Now we know the exponential function is periodic with period 2 pi I. So once we have found one w, we know that w plus 2 pi I also gets mapped to the exact same z value. And so this function starting with a z, finding a w, is not going to be unique. We're going to have to pick which one of these many possible values we want to choose. So how do we do this? Let's write z in polar form as the norm of z times e to the I theta, where theta is an argument of z. And let's write w in Cartesian form as u plus iv. Then e to the w is equal to z becomes e to the w is equal to absolute value of z e to the I theta, because we wrote z in polar form. And since we wrote w as u plus iv, this then becomes e to the u e to the iv, which is just e to the w, equals norm of z e to the I theta. Here we see two complex numbers in polar form. When are two complex numbers in polar form the same? Well, their distance from the origin needs to be the same, so e to the u needs to be the same thing as the absolute value of z, and their angles need to agree modulo 2 pi or 4 pi or multiple of 2 pi. So v and theta need to agree up to a multiple of 2 pi, which means v needs to be an argument of z. We therefore can define the following. We define the logarithm of z with an uppercase L to be the natural log of the absolute value of z plus I times uppercase argument of z. And that's defined to be the principal branch of the logarithm. Remember, I told you we have many choices for the argument of z. If we choose the principal argument of z, then we get the principal branch of logarithm, and it's defined as the natural log of the absolute value of z plus I times uppercase argument of z. Furthermore, lowercase logarithm of z is ln absolute value of z plus I times argument of z with lowercase argument is a multi-valued function. It allows all possible values for the argument down here, and it can be obtained from uppercase argument of z by just adding a multiple of 2 pi I. Both of these functions have the property that e to the log of z is equal to z. Let's look at some examples. So remember, the logarithm of z, the principal branch, is defined as the natural logarithm of the absolute value of z plus I times uppercase argument of z. What is the logarithm of 1, for example? Well, we have to take the natural logarithm of the absolute value of 1 plus I times uppercase argument of 1. The absolute value of 1 is simply 1. The natural logarithm of 1 is 0. Remember, the natural logarithm function looks like this. And it actually crosses the x-axis here at 1. So the natural logarithm of 1 is equal to 0. Plus I times the argument of 1. But the argument of 1 is the angle that the line segment from the origin to 1 forms with a positive real axis, and that is 0. Remember, the argument, uppercase argument, is between negative pi and pi. Let's look at another example. What is the logarithm of I? I is this number right here. Again, we need to find its distance from the origin, which again is 1, plus I times its argument. The argument here is pi over 2. So the logarithm of I is natural logarithm of 1, which is 0, plus I pi over 2. So just I pi over 2. How about the logarithm of negative 1? Again, the distance from the origin of negative 1 is 1. Natural logarithm of 1 is 0. The argument is pi. In other words, the logarithm of negative 1 is I pi. How about the logarithm of 1 plus I? 1 plus I is this number right here. Its distance from the origin is square root of 2. So we get that the logarithm of 1 plus I is the natural log of square root of 2 plus I times the argument. The argument here is pi over 4. So the logarithm of 1 plus I is the natural logarithm of root 2 plus I times pi over 4. What continuity properties does the logarithm function have? Again, here's the definition. Log z is natural logarithm of the absolute value of z plus I times argument of z. Let's look at the parts that this function is made up of. First of all, let's look at the function z maps to the absolute value of z. Well, that's a continuous function. It varies continuously as z varies in the complex plane. The distance from the origin varies continuously. It never jumps. The absolute value of z is a number that is non-negative. It could be 0 when z is equal to 0. Otherwise, it is a positive number, so we can take its natural logarithm. The natural logarithm function is a continuous function, and so the composition of these two is a continuous function as long as you stay away from 0, because the natural logarithm of 0 is undefined. So now we know this whole function here is a continuous function. Now let's look at this second part, the argument of z. Well, we studied that already. We noticed it's a continuous function as long as you stay away from the negative real axis. On the negative real axis, the argument jumps, because we said the argument of a number that's close to the negative real axis is almost pi. But if you're close to the real axis from below, then the argument is close to negative pi. And so as you're crossing the negative real axis, the argument jumps from pi to negative pi, thereby not being continuous. Everywhere else in the complex plane, the argument is a continuous function. The angle that a point forms with a positive real axis changes continuously, except it jumps over the negative real axis. So the argument function is continuous on the complex plane minus the negative real axis. Therefore, the sum of these two continuous functions is continuous wherever both are continuous. In other words, in the complex plane minus the negative real axis. However, the negative real axis is a real issue. As z approaches an x value on the negative real axis, so this is my negative x value, if you approach that point from above, again, the logarithm approaches the natural logarithm of the absolute value of minus x, which is x, plus I times pi coming from above. Whereas if you're approaching this point from below, the logarithm approaches the natural logarithm of x minus I pi. and those are clearly not the same, which means the logarithm function, just like the argument function, is not continuous on the negative real axis. And it's also not defined at the origin, of course. In other words, the logarithm function is a continuous function on c minus the negative real axis, and nowhere else. More is true, in fact. In fact, it is true that the principal branch of the logarithm function is analytic in c minus the negative real axis. We haven't proved this yet. We won't really prove it, but we'll look at a more general fact. But let's first find the derivative of this function. How do you find the derivative? Well, we do know that e to the log z is equal to z. That's how we define the logarithm function. So it undoes what the exponential function does. So e to the log z is equal to z. And we now differentiate both sides of this equation with respect to z. Differentiating the right-hand side is pretty simple. The derivative of z is 1. What's the derivative of e to the log z? That's a composition of two functions, and we need to apply the chain rule. The derivative is thus the derivative of the exponential function, so e to the log z again, times the derivative of the inside, which is the derivative of log z. We don't know what that is. So that's kind of still our question mark right here. But we can now solve this equation for that derivative by dividing both sides of the equation by e to the log z. But what is e to the log z? E to the log z is simply z. So we divide both sides of the equation by z and find that the derivative of log z is 1 over z. Just like it was in real analysis. The derivative of ln x was nothing but 1 over x. So now the derivative of the principal branch of the logarithm is 1 over z. Here's the more general theorem. Suppose that f is an analytic function defined on some set u. So here I drew u down here, and f is this function. And it maps u into the complex plane. And suppose there exists a continuous function g. It's this one down here. That's defined on some domain d. This is my d. And maps d into u. It doesn't have to go onto u, but somehow into u. So here I drew g of d. Such that if I start with a point z over here, follow it with g to g of z, and then apply the f that was defined on all of u, so in particular at this point, I end up where I started, f of g of z. So f is sort of an inverse of g. F of g of z, they undo each other. F of g of z is equal to z. If that holds for all z and d, where the function g is continuous, then g in fact is analytic and has derivative 1 over f prime of g of z. That's our inverse function theorem. It's enough to find an inverse function that is continuous if the original function f was analytic. That guarantees that g is analytic, and we even have its derivative. And this derivative formula is found just like we found the derivative formula for the logarithm function. Let's look at some examples. Suppose f of z is the function z squared. That's clearly an analytic function. We know its derivative, f prime of z, is 2z, and it's defined on the whole complex plane, so u is equal to the whole complex plane here in this case. Let's now look at the principal branch of the square root function. Remember, we couldn't really define the principal branch of the square root function on the entire complex plane. We had the same issue. We had to cut open the complex plane, take away the negative real axis, for example, and that made the principal branch of the square root function a continuous function. Remember how that was defined? The principal branch of the square root function was defined as taking the square root of the absolute value of z times e to the I argument of z over 2. That's the principal branch of the square root function. And again, because the argument function is continuous in the complex plane except on the negative real axis, this function is going to be a continuous function in the complex plane minus the negative real axis. And f of g of z is equal to z for all z in the complex plane minus the negative real axis, because if I take the square root and then square a number, I'm at the number that I started with. So if I start with a point over here, I take the square root, which is going to put the number somewhere over here, and then I subsequently square it again, I end up again where I started, namely over here. G is a continuous function, and by the theorem it's therefore an analytic function in D, and its derivative is 1 over f prime of g of z. But f prime is 2z. So that's 1 over 2 times g of z. And g of z was the function square root of z, so the derivative of the square root function is 1 over 2 times the square root function. That's exactly the same that we had in calculus for the derivative of the square root of x. But this time it's this principal branch of the square root function, which is defined in the entire complex plane. We have to exclude the negative real axis because the function was not continuous across the negative real axis. Let's look at another example. F is the same function as before. F of z is z squared. Again, the derivative is 2z. Again, we define an inverse of this function, but on a separate domain. We're going to define a function that is continuous, but this time we want it to be continuous on the domain d tilde, which is the complex plane minus the positive real axis. If we wanted to define a square root function here, let's figure out what the square root of z looks like. All square roots of z have the form square root of the absolute value of z times e to the I argument of z over 2 plus optionally I pi. Since e to the I pi is -1, we get two possibilities for the square root function. It's plus or minus the square root of the absolute value of z times e to the I argument of z over 2. In other words, that's plus or minus the principal square root of z. Those are my two choices for square roots for a point. So now I want to define a square root function on the complex plane minus the positive real axis. If I choose the regular square root function on the upper half plane, then as my z's approach a point -x on the negative real axis, the square root of those points wants to be on the positive imaginary axis. So if I wanted to continuously continue this to the lower half plane, I cannot choose the principal branch of the square root function, which maps points close to the negative real axis to the negative imaginary axis. Instead, I need to choose the negative square root function on the lower half plane and the positive square root function on the upper half plane. And that's exactly what we're going to do. When the imaginary part of z is positive, we choose the square root of z. When it's negative, we choose the negative square root of z. This function has the property that it is continuous on the negative real axis, but it's going to have a jump somewhere, and that jump is going to happen on the positive real axis. That's why we need to exclude the positive real axis, because as z approaches a positive value on the real axis, the square root of z approaches a real value that's on the positive real axis, but minus square root of z as we're coming from below will approach a value on the negative real axis. So this function h of z is not continuous across the positive real axis, but continuous everywhere else in the complex plane. Again, if I square either of those values, square root of z or minus square root of z, I get z. So f of h of z is z for all z in the plane minus the positive real axis. H is continuous in this new domain, and therefore by the theorem this function h is also analytic in d tilde, in this plane minus the positive real axis, and its derivative is 1 over f prime of h of z, which is 1 over 2 h of z. So this function h of z right here. So that is equal to 1 over 2 square root of z if the imaginary part of z is positive, and 1 over minus 2 square root of z if the imaginary part of z is negative. Let's finish up by just remembering some terminology. Given any function f from some set u to a set v, and this doesn't have to be in the complex plane, this is general terminology. We say such a function f is injective or one-to-one, provided that whenever you start with two separate points a and b in your set u, they get mapped to separate points f of a and f of b in your set v. They cannot be mapped to the same point. So if that is the case, then we say the function is injective. If a and b get mapped to the same point, the function is no longer injective. But if for all possible combinations of a's and b's that are not the same, f of a and f of b are also not the same, then f is injective. F is surjective, also called onto, provided that no matter which v you start with, you can always find some value in u that is mapped under f to that v value. In other words, every value in v is an important number. It is hit by some x value. It could be hit by more than one x value, but there's at least one x value that is mapped onto this y value. F is a bijection. We also say it's one-to-one and onto if it is both injective and surjective. Let's look at some examples. The function z squared is a bijection if I choose my domains appropriately. So here I chose for my u the set of all z's whose real part is positive. So my u is the right half plane. And my v that I chose up here is the whole plane minus the negative real axis. So I'm taking away the negative real axis. And the claim is that the function z squared is now a bijection from u to v. Whenever I choose two distinct values in u, they're going to be mapped to distinct values in v because I've restricted my function to the right half plane. We know that the function z squared is typically not a bijection because for every point I can just choose the negative of that point. When I square these two, they get mapped to the same value, somewhere over here. However, I'm not allowing any point and its negative to be contained in my set u at the same time. Therefore, that makes my function z squared injective. Moreover, every point in v has a preimage. I just divide this argument in half and take the square root of the distance from the origin. By dividing the argument in half, everything lands over in the right half plane, and there's in fact, for every point in v, I can find a point in u that it came from. And therefore, that makes this function z squared a bijection from u onto v. If, on the other hand, I allow u to be the entire complex plane and v to be the entire complex plane, and look at the function z squared between those two, well, it's not injective, as we saw before, because for every point z, there's another point z that gets mapped to the same point over here. But it is surjective, because for every point in the complex plane, I can find a square root that is coming from somewhere over here. So it is surjective, but no longer injective. Finally, if I do restrict my u to c minus the negative real axis, and I allow v to be the entire complex plane, and I look at the function square root of z, I know that function is injective. No two points get mapped to the same value over on the right-hand side on the square root of z, but it is not surjective because all of this under the principal branch of the square root function gets mapped into the right half plane. And so any point over on the left does not have a pre-image under the square root function where it would have come from. So no point in the plane minus the negative real axis gets mapped to the left half plane under the principal branch of the square root function. So that's enough for today. Next up are conformal mappings, Mobius transformations, and looming in the distance, the Riemann mapping theorem.